Hello, everybody. My name is Philippe Giguère. I'm a professor at Laval University in Quebec City, Canada. And today I'm here to present some of the work we've done relating to the application of AI and 3D mapping to the forestry industry. Maybe as a motivation here, why do we want to automate forest operation? First of all, it's the most dangerous job in North America and by far. And also, if you talk to a forestry operator, they have definite issues about labor shortage. It's been very hard to recruit talent to operate forestry equipment, such as harvesters, for instance. Also, the training period is quite long. For instance, the productivity peak is reached about after 8 years of operation for a human operator. Oftentimes, they lose their employees before that 8 year period is reached. Also, there's issues about maintenance. These are fairly heavy and powerful machines, and junior people who operate these machines tend to break them a lot more than more senior people. Also, by having automation, you're able to predict better the harvest amount of wood that you do. Also, I think right now we're in a very good spot. We have this technological convergence where we're starting to see affordable 3D sensors, such LIDAR, stereo camera, or time-of-flight cameras. Also, there's a fairly large number of algorithms which have appeared recently, like such as deep learning and 3D mapping technology, and also GPUs, which now allow to do a fair amount of CPU treatment, not CPU but GPU treatment, processing power on an embedded device. So all these things together makes that I think the time is right to really go and explore how can we automate some of the forestry operations. And why are we researching it at Laval University? I'm not a person who was doing forestry when I did my PhD, for instance, but there is a very nice research consortium at Laval, which is called FORAC. It's basically means from the forest to the customer. It's a research consortium that has been operated for about now something like 15 years. And it has trained a large number of highly qualified personnel, like PhDs and master students, and a large number of professors, like 22 professors and 4 research professionals. But this creates a good bridge between research at the university, but also with private partners. And it's through knowing some of the people who are part of this organization, they approached me and they basically what I found is people in forestry or the forest offered very interesting challenges to robotics and artificial intelligence, and that's how I got interested in doing forestry, forest-related project. Also, we're very lucky in Laval University. We have access to the Montmorency Forest, which is the largest teaching and research forest in the world. It covers an area of about 400 square kilometers, which is the size of the island of Barbados, and it's quite close. It's about 45-minute drive north of Laval University, and it has good facilities. For instance, like 50 bedrooms, a cafeteria, and so on and so forth, garage, cottages where we can deploy our teams and our robots. It's also an ideal test bed if we one day we want to really push the experiments about automating the cutting of trees, because we're allowed to cut trees uh, on that research facility. Now, the overall plan of this presentation is I want to discuss some of the recent how can we leverage the recent progress in artificial intelligence and mobile robotics to further the automation in the forestry industry. And in particular, I will discuss some of the works we've done. First, some work I've done with the DAMAS laboratory, where we applied deep learning to bark images, and we did two specific tasks there. First was species identification, and then tree re-identification, which is basically using the tree bark as a fingerprint, if you want, to be able to recognize individual trees that we've seen previously. Also, I will further discuss the use of 3D mapping with using mobile LiDARs in forest environments, and particularly projects that I've done in collaboration with Nibio and now at Norlab about doing forest inventory, in particular estimating the diameter at breast height for a patch of a forest, and finishing this presentation by onward-looking project that we have started last year, which is about the partial automation of forest reparation, where we are looking at automating simple tasks. No, not necessarily simple tasks, but very precise tasks, not the whole. We don't want to automate the whole system, just looking at automating part of the operation. So one would be the cutting and grasping of trees or logs, and then doing guided navigation to automate or reduce at least the cognitive load of people operating forwarding machines. So let's start with discussion of how can we apply deep learning to bark images. So why use bark images? First of all, they're rich in texture, which gives a lot of information, and also a lot of computer vision algorithms are good at working with texture classification. Also, from maybe a practical point of view, they don't change a lot over months. The appearance of bark is not something that evolves rapidly compared, for instance, to foliage. Also, the bark is persistent throughout seasons, and if you cut logs, then you can also use possibly the bark for re-identification, although there is definitely some mechanical damage that will be done by the rollers on the felling head. But also, I thought it was a very interesting scientific question. What can you do? Can you recognize species? Can you recognize individuals based on these bark images? So the first project we did was with Mathieu Carpentier, which was a master's student, and you looked at doing species recognition on bark images. And that was followed by, if you want a more I don't want to say precise, but a more uh, narrowed uh, idea, which was, okay, now that we know we can recognize species, can we actually recognize individual trees or actually individual tree surfaces using deep learning? And that was a project, the master thesis project of Martin Robert. Now, going on to the species ID classification, we thought that it was also a very challenging vision problem. You have here the picture of three different bark surfaces on the left, and then you have also three other bark surfaces on the right. And what it is that makes this problem interesting is you can see that the pictures on the left corresponds to three different species of trees, whereas the pictures on the right correspond to the same species, but trees of different age or different DBH if you want. So that creates this very interesting vision problem where you actually have sometimes less interclass variation than intraclass. The first thing you need to do when you do machine learning, and particularly deep learning, is you have to start collecting data, a lot of data, to be able to both train your system and also validate that it is working. So what we did with Martin, not Martin, sorry, but with Mathieu and a number of other interns, for instance, we hired somebody from Forestry department to do the species identification. So what we did is we went around the campus, but also around forests in the nearby area, and we identified 23 different species from the eastern side of Canada that we could use for our experiments. Most of these species have some kind of commercial value as well. In total, we curated our data set down to 23,000 images, but the initials we had to take about 35,000 images. But there's always a bit of bad exposure, motion blur, and so on and so forth. So I had to manually curate that down to about 23,000 images, which correspond to about 600 to 2,600 images per tree species. And all of these pictures have been selected, but also cropped such that we only see the bark, we don't see the background image, particularly for trees which were pretty young, because then it means that the tree is narrow and doesn't occupy the whole space in the image. That dataset is freely available. I put the link down there if you're interested to find the sublinks that indicates where to uh, go and gather this data set. It's fairly large, about if I remember, about 15 or 20 gig in total. You have here a quick glance of what the data set contains in terms of species. So you have the picture of the 22 different species, and on the left you see the names and also the number of trees. For instance, we have certain trees that, like we see here, white ashes. We have 61 trees that we collected data on, and that generated about 1,472 pictures. And also, it's something I feel it's important when you do data sets, particularly again for deep learning, is it's not an open loop process where you go and collect data and then you curate it and then use it. It's more of an iterative process where you go and you start collecting some data. Then you start training your networks, for instance, and you want to look. But what you're looking for is what are the species which are hard to identify. And when you see that some species are hard to identify, for instance, with some difficulties differentiating between red maple and sugar maple, they look fairly similar. So what happened is we end up having to collect more data, more trees, more pictures as well for these two species to be able to, if you want, gather more knowledge. Other species which are easier to distinguish, we had to collect less data. But it's something I think is important to understand. Don't just go out there blindly collect data. Really pay attention, and over weeks and months, make sure that you're collecting the right data, because there's if you collect a lot of data on species which are easy to identify, but in some sense you're kind of wasting your time. So it's maybe a word of advice out there if you're interested in doing the same thing on your side. So if we look at the results we had for the classification, we use two different network architectures. We use a ResNet 18 and 34. At the time, they were state-of-the-art networks. Obviously, if we were to redo the work today, we would use newer networks such as DenseNet and the likes. Good practice, you always use the networks which have been pre-trained on ImageNet. You get a few percent difference if you do that compared to just using a randomly initiated network. So important always take the ImageNet version, pre-trained the version which has been pre-trained on ImageNet. So we did a couple of experiments. So imagine you have your trunk here, and you take a number of pictures on that trunk. So the first experiments we did is what are the performance we get when we take a single crop, a 224 by 224 crop, and we look at classifying the species based on that single crop. So the performance were okay, that's not so bad. So again, it was over 20 different species. There's 3 species we didn't use because we just didn't have enough pictures. So we get about 86, 87% performance in terms of precision of recognition. Then you can say, okay, well, let's take all the possible crops, non-overlapping crops in a single image of the trunk. So you give this approach where you basically do a voting system, where each crop you vote for the species you think it contains. And on the example here, it's a white birch, and you 6 correspond to the ID of white birch. So you see that if you were to do a majority vote, then 6 wins from all the crops. And indeed, it was the correct answer. So by doing this concept of one image, multiple crops, and doing a voting, without big surprise, the results start increasing. What became more interesting is, okay, let's push it further. Let's compare, taking a single crop, random crop in all the images that we have for a trunk versus taking all the crops of all the images for a given trunk. And what we see is actually there's not a huge performance difference. It's within the, let's say, it's not statistically significant the difference between the two. So we like to think that basically it gives the same performance whether you take a single crop for all the images or all the crops of all the images of a single trunk. So it's probably the idea that as long as your crops are spread over the trunk as much as possible, to if you want to observe a lot of area on the tree, on the trunk, then you get good results, because the chances of hitting a crop which is not very informative reduces. So that's a bit of a take-home message we have here is maybe you don't need to look at all the crops of all the images, but just a handful of them, but spread over all the images. Another thing we looked at, because as I said, collecting data is very expensive, so you want to make sure that you do the right thing. Yeah, just as a side note, it was about 6 months of work to collect data, curate it, and analyze it. So it's a large investment in time. So what we did here in this experiment is we decided to decimate the data set. So we would reduce the size of the training data set, train the network, and look at the performance that we get. And you can see at the bottom here is the percent, the fraction. So it shouldn't be percent, but it should be a fraction. So 0.1 would mean that 10%, and here we use all of the training data set. So obviously, as you reduce the size of the data set for the training, the accuracy will decrease if you want, like in a elbow manner. But what was very interesting is if you decimate the number of images, but you try to keep the same number of trees in your data set. So basically have pictures taken from a maximum number of trees, but not necessarily a lot of pictures per tree. So maybe like having 1 or 2 pictures per tree instead of having, 20 pictures coming from the same tree. So what we see is, and that's the situation here in blue, that's where we have a lot of variety in terms of individuals, as opposed to here where we don't have as much variety. And what we see is it's more important to have a large variety of individuals in your data set than actually, having a large number of images. So that, in some sense, is an important point here. Is the number of trees really important for your training data set? And in some sense, if we were to further collect data, that would be a direction I would head, is taking maybe less pictures per tree, but try to have more trees. And it's also important because there'll be the disk space used by your data set, but also the training time. Your network has to go and look at these images, and if you have a lot of images from the same tree, basically, as you're wasting a little bit of your GPU cycles looking at images which are somewhat similar, because the trees, that particular individual has features which are visible in other pictures. Now that we've demonstrated in some sense that you're able to recognize species or identify species from bark images, we wanted to go, okay, let's push this a little further. Can we actually re-identify an individual tree, or if you prefer, an individual surface, a patch, using the bark unique texture as a form of signature? And what can it be used for? For instance, if you're doing a SLAM system, you have to have landmarks. Like you have, you see here, for instance, A, B, C, D, and E, which represent physical landmarks in your map. Then to be able to associate your measurements with the landmarks, you have to have some kind of signature. So here you could basically keep pictures of the bark as signatures, and being able to actually recognize an individual tree you will be able to associate some measurements with specific tree landmarks. So that could be something very useful. You can also imagine maybe for a system where you want to track logs which have been felled using, again, the bark signatures, although this might be a bit more difficult given the mechanical damage that can happen to the surface. But anyway, it could be interesting to as an application for this kind of work. But the bottom line was, question was, can we actually re-identify an individual tree from that bark signature? That's the key question we're asking ourselves here. And just to give you a bit a flavor of the challenge, you have here six pictures of physical surfaces of the trunk, so bark images. And the idea is you have to match the pairs, because there's only actual 3 surfaces is here, but they've been taken with different illumination angles, and it's definitely not easy to match the images together as pairs. But I'll give you the answer. So we have, for instance, these are the 2 same surfaces but different illumination. The tree B is here, and the third matching pair is here. And it's, once you have the answer, you kind of look, for specific details on the bark, and you kind of play this Sherlock Holmes game where you look at clues where you can use to actually be able to do those matches. And I'll give you some examples here. You have probably like a knot that was coming out of the bark here for the, that could be a way of matching the pictures that correspond to the tree C. And you have here, for instance, a place where the flake was removed from the tree. So that's another thing you can use maybe to match the pair for the tree A. But it would be a very tedious game to play, especially if you have like thousands and thousands of pictures that you have to compare to find, if you want, matches between different images. I like to think of it as basically a fingerprint that you have. Fingerprint has the same problem. You have databases of millions, hundreds of millions of fingerprints, and it's the same thing. You're not going to go and compare pixels by pixels. What you're going to do is look for specific features in your fingerprints database, and then you'll be matching fingerprints based on the presence, absence, location of these various features that you have. we use the deep learning approach to develop basically a descriptor, which is, if you want, a local signature of an image patch to be able to solve this problem. The advantage of using deep learning is it's a data-driven approach. So whatever data you feed the system, it will specializes on that type of data. So because we fed our system with BARK images, then we were able to get it to specialize to BARK images. Again, we had to go and collect data. So we collected 2,400 BARK images. And we had to be very, very careful here on how we collected our data, because you have to be, if you want, you have to give your network some kind of implicit information about these. What is this the problem you want to solve? And here we wanted to solve the problem for BARK images with illumination changes, because you never know where the sun's going to come from if you have to identify a tree. So what we did is, we had to make strong illumination artificially by taking pictures at night, moving a flashlight, that we would get strong illumination changes. And also, as I will discuss later, we had to pixel align the images for training purposes, which was quite, I would say, quite involved. But Martin did a fantastic job at doing so. It's really, I tip my hat to him for doing that. So if you can look at one image that would show the comparison between using deep learning descriptors versus using more classic descriptor like SIFT or SURF, or DeepDesk, which was a deep learning descriptor which used a much simpler network, then you can see that we have for descriptors. I won't talk too much about SqueezeBark because it's a simpler version of the network, so I'll mostly focus on DeepBark. But you can see that, so you have here image A and image B, so that's the same surface, but with strong illumination changes. You can see here, for instance, there's a ridge, a shadow that is not appearing here. And you can see that the matches between the left and right here, so the matches between the two images, we have a lot of matches for our descriptor. Compared to the traditional SIFT or SURF, you see that there's a very poor number of matches between the two images. So it makes it not a great choice to be able to re-identify images, because that's what we're going to use basically, is the number of matches as a way of determining if we have a good match between two images. And if you don't have a lot of good match in the first place, then it's not working very well for your system. So again, a few words about data gathering and training. It's something that you spend a lot of time when you do machine learning, is to make sure that your data set is correct and doesn't contain too much biases, because there's always some biases, but you want to minimize them. And again, Martin did a fantastic job. He came up with that idea of, to do the pixel registration. So he built a wooden frame, and he put 4 fiducial markers, and then he used that wooden frame to basically help with the image registration process. So basically, also for the as I explained before, for the illumination changes. So what we did, we took the pictures at night. You can see right here the black, very dark background, and we just simply moved the flashlight while we take the pictures, such that we could have strong illumination changes on the bark. So our dataset contains 12 pictures. So Martin would place the frame on a given physical patch of the trunk, and then he would take 12 pictures of that particular patch, and he did that twice for each tree, and then he just changed tree. So in total we have 12 pictures for 100 surfaces of elm and 100 surfaces of red pine. So a total of 2,400 images. And as I mentioned earlier, the fact that we had these fiducial markers, which are easily detected by computer vision libraries, allowed us to do the registrations between all the images, what's called the homography. So being able to translate, if you want one image into another one, quite easily and in a fairly automated manner, such that, for instance, you have this red patch of image, then it's easy to find the corresponding pixels in the next image and on the third image that correspond to the same physical location in the tree. And that would be essential for training of our approach. So in the end, what we want to have is a descriptor. So we're talking about descriptor space here. We choose the dimension of 128 for our descriptors. So what you want to have is for two patches that correspond, two images that correspond to the same physical patch as illustrated here, you want their descriptors to be fairly close because they represent the same location, even though their appearance might be different. And on the other hand, for a randomly selected patch in the image, you want that descriptor to be far away from the two others. For the extraction of the descriptor, without great surprise, I've already mentioned it, we use deep learning, so ResNet, for instance. And the technique you need to use to be able to achieve this kind of behavior where you want to have things which, some things that need to be close and some things that need to be far, but we don't actually care exactly where they sit in the descriptor space. It's, it's a vector that we don't really care what it represents. All we care about is surfaces of the same, descriptors of the same physical surface should be close and others should be far away. That's the only thing we require. And metric learning is actually the tool you use to solve this issue. And with networks, what you need essentially to do the training is a loss, and we use a loss which is similar in spirit as the one I show here. It's called the triplet loss, and basically the idea is you want to minimize this loss, and this loss is, you have a max. Simply, the max is simply such that you have a zero here and a term here. It's such that the lowest value of this loss will be zero if you want. It's like a ReLU. And you have A here is for what's called an anchor. P is a positive, so these two correspond to the same physical surface. And then you have the negative example. And the triplet loss, basically what it does is you want to, you see here, you want to, of course, I recall this. We have to minimize this cost here. So basically is we want to reduce this value here as much as possible. So that's the Euclidean distance between these two descriptors. That would be the distance between these two dots here. And then you want to maximize this value here because there's a minus sign here. So you want to maximize the distance between the anchor and the negative value up to, if you want, a margin which is called alpha. So that's what this loss allows you to do, is develop a network that will, you show it a patch, it will spit out a descriptor, and the descriptor hopefully will allow you to do this correspondence. If you look here, you have examples of training patches that come from our dataset. Again, recalling that we have 12 pictures that we took of the same physical surface. So here I show 4 key points. Key points are points in the image where they're salient, and that's usually where this, for example, instance, a corner or something, and then that's around these key points where you extract the various descriptors, and then we use these as training data sets and applying this triplet loss that I explained previously. So once you have trained your descriptor extractor, which we call DeepBark, so what you do is you go ahead and you extract what's called key points. Again, the key points are a salient point in the image, and around each of these key points you will extract a patch, a 64 by 64 pixel patch, and then you feed that patch to the DeepBark network, and at the output we have, it's basically a ResNet 18, and we removed the classification head and replaced it simply by a fully connected layer with 128 outputs, which correspond to the dimension of our descriptors. And so that gives you this vector, so this descriptor associated with that key point. And of course, you have more than one key point on the image, especially with Bark images. They're very rich in corners, so usually it's no problem to find 500 key points. So that spreads, if you want, these various descriptors around the image. So at the end, what you have is a collection of descriptors, maybe between 300 and 500 per Bark images. You also have their location in pixels in the image, which helps you do some further testing to eliminate bad matches, for instance. The query process is as follows. So we have what we call the test set, which is the collection of all the Bark images we have, which could be up in the 10,000, for instance. And then you have a query, which is, you give it an image. What you do is you start comparing all the descriptors from this first image with the first image in the test set and the second one and so on and so forth. And you see in green here, these would be matches in the descriptors which are considered as being valid, and what we use for validity test is the low ratio, which is the same which is used for SIFT. Basically, is if the distance between the first matching pair and the second matching pair is great, then that's usually a good indication that this first match is a good one. Also, you can use geometric verification, which was, if you want, make sure that the locations of the where the matches are found make sense between the two images. I won't talk too much about this, but it's just another possible test, but that takes into consideration the location of the features of the descriptors on the image itself. And yeah, we see another query, another example where it's the same query, but here I applied the first image of the test set. You have to do that for all the images, so it's quite time consuming. The goal here was not to reach real-time performance, but just to see, can we actually do it? And you see, for instance, for this other picture in the test set, you see a large number of valid matches, with here like two bad matches. So clearly here you have a sense that these two images must be coming from the same physical surface, and that's exactly what we do. Is we rank the results by number of good descriptor match between a pair of images. So if we have let's say 250 good matches in an image and we have 500 descriptors, there's a high chance that this is a good. Basically, these two images correspond to the same physical surface, same bark area, if you want. So in the end, we're very happy with the results. The performance were actually quite good. You have here the famous precision recall curves, and what's important to know is we had 11 positive examples in our database, and then we had a certain number of negative examples. For instance, we have tests at 1,200 negative examples, 2,800, and 7,900 negative examples in the database. And what we see is the recall, the precision is quite high for the recall. Of course, there's a bit of a drop here towards the end. A perfect precision recall curve would be basically all the way one everywhere, and then it's basically this very squarish curve. So we're getting close to that squarish curve, and that's much favorably compared to SIFT descriptor. You see here the SIFT is quite lower. The other thing that was very interesting that we found is, even though we keep adding more negative examples in our database, you see the curves here are pretty much overlapping for or DeepBark descriptors, but you can see here that SIFT is increasingly struggling as we had more and more negative examples, which in some sense was also a sanity check to make sure that there was no bug in our methodology, but it really basically bodes well for this approach of deep learning for recognizing different surfaces. So we're very happy with that results. Yes, it's possible to re-identify a tree based on its bark signature. Switching gears a little bit, so here we're going to start looking at how we can apply 3D mapping technology with mobile LIDAR to do specific tasks related to forestry. And we looked at doing inventory more precisely, to looking at how we can use that technology to do DBH estimation. There's definitely certain advantages of using a terrestrial LiDAR for forest mapping or inventory. For instance, you have a good view of the trunk, so you can have a good geometry estimation, which in turn can be useful for when you do precision harvesting, where you want to collect certain trees with certain geometries to fill a basket of orders, as opposed to aerial or LiDAR, which doesn't usually have a good information about the trunk geometry. But the data capture process is a lot more involved, a lot more cumbersome, because you have to actually navigate in the forest, which is sometimes very, very difficult. For us, it makes it very interesting from a science point of view, because these are, one can claim, they're somewhat GPS denied, which is often a topic or a condition that which is used for research in mobile robotics, where you expect that you don't have access to GPS, because if you're on Mars, there's no GPS. So a lot of mobile robotic research is done precisely with that condition of GPS denied. Also, it's not the idea of okay, let's get fleets of robots that go and harvest data in the forest. I'd like to think more of the concept of opportunistic data gathering, where it could be, for instance, you have a worker that walks in the forest already. Why, you just strap a backpack on him with the LIDAR, and then he collects data. If you want no cost, the person had to go walk there for some reasons. Or it could be the equipment which is mounted, the sensor suite, which is mounted on the forestry equipment itself. So the driver is, if you want, in charge of moving the sensors, because they're actually moving the equipment to accomplish their own task. But on the fly, you could be building a 3D map of the environment at very low cost in that case. And it's something very important if you're looking at automation. Maps are nearly essential when you're trying to automate systems. In our situation, for instance, it could be the tree selection and cutting, or the path planning and navigation. So if you don't have a map, it's nearly impossible to perform good automation. So I think something that has been explored, this concept of doing path planning and automation in previously. Like I like to think about the similar work done by Elstrom and Ringdahl. It's this the precursor work where they looked at what can you do with the technology that was able at the time to do these the automation of forwarding, for instance, using path following. First work I was involved with in terms of mapping in the forest it was the students from Nibio in Norway. It was Marek, and we worked together on this project. He obviously did the majority of the work, but the idea wanted to explore how can you make a small robot that goes and explore the a forest to try to build a 3D map of this world, of this environment. And he set his sight on using GraphSlam algorithms. And so he deployed his robot in a semi-structured environment. I say semi-structured because it was not like a very harsh forest, because the platform was itself was not developed for harsh environments. And he did experiments was doing a trajectory of about 130 meters, where he collected enough scans to rebuild 3D models of 71 trees, and he was able to do DBH estimation for these 71 trees. And there was a number of assumptions that were made in this work. One of them was that the trees would be vertical, such that you can, so if you want, reproject some of the point clouds. You take a slice of the point clouds, you project into a 2D surfaces, because you assume that they're vertical. The trees are vertical, and then you can do DBH estimation by doing a circle fit on this collapsed view of the environment. You have here a picture that the platform that I tipped my hat to Marek. He's actually the one who built this platform from scratch, so it was pretty impressive that he was able to achieve that. And he used a VLP-16 LiDAR for the data collection. You have here the map that he managed to build with his platform, and you hear the lines here is basically the trajectory that was followed by his robot. And he was able to establish that using this kind of approach, he was able to have a relative tree positioning error of about 5 centimeters, and for the DBH about 2.4 centimeters error of estimation. We investigated what are the various factors impacting this DBH measurements, and one that we found was key was what was called the support ratio. And the idea is, some trees, for instance, the tree here, you have this collapsed 2D view. So if you want, like if you were to put your camera right above the tip of the tree, so yeah, this reprojection of the points on the 2D surface. So trees which are located, for instance, in this area, when the robot goes around like this, they only get painted. The LiDAR only paints one side of the surface, so that's why you have these points here. And the support ratio basically is what's the angular fraction, of the arc here compared to a full circle that has been painted by the LiDAR. So here you have just under half of the circumference of the tree which has been painted by the LiDAR, as opposed to other trees. The trees, for instance, located inside the loop, these have been painted from all sides, so these will have a nice support ratio of 1, where basically the entirety of the tree has been covered. And we found that this support ratio does impact the DBH estimation. So you see, for instance, if you have very small support ratio, then you tend to have a overestimation of the DBH, and as the support ratio uh, increases, then this positive bias disappears, and we're not quite sure why we had this negative bias here. But the point is, you see this is definitely a trend between the support ratio and the error of the DBH. We followed up this work at Norlab at Laval University with doing, if you want, a more exhaustive experiments in terms of DBH estimation. So what Jean-François did is collected data over 4 different environments, and he really pushed a number of trajectories. He went to 11 trajectories, and also we used a all-terrain robot to be able to do mapping of unstructured environments. It was quite challenging at times for the robot, but the robot was able to navigate. Obviously, it was guided by the human, but the robot was physically able to traverse the terrain. And in the end, it was able to map a large number of trees, 943 trees over these 4 environments. And also, you wanted to go really a full 3D approach, so no assumption of verticality for the trees. So in this case, you cannot just reproject the points on a single surface. You have to actually go do something like a cylinder fitting to be able to recover the DBH. And also, we wanted to see how far can we push a non-SLAM approach, so just LIDAR. It's called LIDAR odometry. So we use a package called LibPointMatcher, which is maintained by our lab. It's basically the brainchild of François Pomerleau, which is the head of Norlab. We use this platform called the Husky A200. So that's a robot that is all-terrain. It can carry up to 75 pounds, I think, or 75 kilograms of payload. And the main sensors we use for the mapping approach was the using of a Velodyne, the HDL32E, which was a loan from the Canadian Space Agency. And so thank you for that loan. And we use as an IMU XSense MTI 30. You have here a picture of the 4 test sites that we use, so you can see definitely the unstructuredness, particularly in this young forest. So there's a lot of undergrowth, so this was quite challenging. You have the mixed, so a mixture of deciduous and evergreens, a more mature forest, and then you had a maple forest located on our campus. So FM is basically for Forêt Montmorency, and UL is for Laval University. And here you have the various areas, the number of trees that were on each of these sites, the stem densities, and finally the length of the different trajectories and the number of trajectories that were done for each of these environments. So just to give you an idea of how involved these tests are, a single trajectory would basically it would be a day of work just to get there, drive the robot, and then clean the data. So it was very, very involved in terms of experiments. You have here a video that shows both you see on the right hand side, you see Jean-François driving the robot with the joystick. So again, this is not an autonomous system. It's the robot is guided by the human, and you see the map, the point clouds being reconstructed, and the arrow is basically the state estimate of the position, so the orientation and position of the robot as estimated by the mapping package. So what he did is basically first reconstruct the 3D environment, and then he found a digital terrain model to be able to find what's the elevation, because once you have segmented your trees, you have to be able to pick the points which correspond to the breast height, which is about 1.4 meters. And you want to, of course, not just collect the points which are exactly at that height, because you'll have only a handful of points. So you want to keep a little bit of points above and below this breast height. And that's what you get here. It's just this selection. So you have these, if you want, these little fuzzy cylinders that float up in the air, and that's these fuzzy points fuzzy clouds that we'll be using for doing the DBH estimation. A big question that was there is, which primitive should you use to be able to do this DBH estimation? So there's a large number of models you can use, going from circles to the full generalized cylinders to do your 3D the DBH estimation. But obviously, the more parameters you have, well, the more sensitive you are to overfit on your data. So we focus primarily on cylinders, which is something that also others have noted in the past. But the question that we then remain is what's the best way to fit cylinders on these data points? So first of all, should you use a single cylinder to match the remaining point clouds that we grab around the breast height? Should you take 3 smaller cylinders spread over these points and then you do the mean or the median? Or should you use 5 cylinders and then do the mean or the median of the DBH estimation for each of these cylinders? So in the end, what Jean-François found is that the best approach is to actually take the median either of 3 or 5 cylinders, and that gave good results. For instance, we had about 2 centimeters error for DBH estimation for the mature site, so compared to 3.45 if we look at the whole data set, because this imprecision might be coming, for instance, from mapping errors or just the LIDAR itself. Another interesting point was we found that there was a negative bias for maples, which is most likely caused by bog texture. They're very, very deep textures. We also found another take-home message, which is you got to stay close to your trees if you want to do a good DBH estimation. You see here what's the minimal observation distance. So if you're within 0 to 5 meters or 5 to 10 meters, the DBH error tend to be fairly small. But as the minimal observation distance increases, you can see that the spread increases tremendously, and it's even more visible if you have leaves on your trees. You see how the error is much more spread for the DBH with the leaves on. So given all these exciting results that we got previously, we're now looking at starting to do partial automation of forestry operations. And the two aspects that we will be exploring in the coming years is the cutting or grasping of tree or logs, and also guided navigation for forwarding. So to explore this concept of automating basic forestry operations, we have obtained a grant for 5 years. And here the objective is not to do the 100% autonomy. We're really looking at, reducing the cognitive load of operators, such, for our harvester and forwarders. And in this project, we'll have like 1 master's and 2 PhD. And a bit of shameless plug here, we're looking for ways to have 1 PhD slot, which is open. And this grant covers 3 sub-projects: expansion. We want to continue expanding 3D mapping in the forest environment, also looking at cutting trees or collecting logs using AI, and finally, how can we apply guided navigation robustly using teach and repeat for forwarding. So the 2 aspects I will discuss today are number 2 and number 3. Beta may be a presentation for the lab in which we'll be conducting this research. So it's the NOR lab, which was founded by François Pomerleau, which is the director. I'm the co-director of the lab. So it's a recent lab. It only has 3 years existence. And we specializes in mobile autonomous systems working in northern or difficult outdoor conditions, which is in the case of the Canadian forestry industry really fits this bill description. And what we're interested is investigating new challenges related to navigation and perception algorithms, again, which is very, very important for the forestry industry. And what we'd like to do is really push the boundary of what's possible with the current technology and basically try to expand the state of the art through these challenging problems. And to this effect, we have a nice suite of equipment that we've started to build up. So we have our a robot arm here. We also have the ClearPath Husky you've seen previously, and we've recently acquired a ClearPath Warthog, which is it's not as big as a harvester, but it started getting a bit more scaled up and has great mobility. And also we have Trimble robotics total stations if we want to be able to do precise measurements of the location of our robotic equipment. And to this effect, also we have active prisms that we have we have mounted on the robot. And of course, the robot is equipped with a fair number of LIDARs and cameras and sensors. So the first aspect is cutting trees or collecting logs. And it's always important when you do a project, always find the right abstraction to simplify it as much as possible. So here you have a bit of a cartoon figure. Imagine this is your harvester, and you have a sensor here, and you know the what's the transformation between the sensors and the main body of the harvesters. And of course, your head and your arm must be, you know, you must have the sensors to be able to know what's the position of the head regarding the the the, the center of mass of the vehicle. So in the end, you have this nice kinetic chain. And with your sensor, you sort of go and paint the environment, where here you have a little tree. And if you're able to locate this tree within the sensor field of view, well, basically with the kinetic chain, then you can go and plan the path to go and grab the tree with here we use a feller buncher as the device that we want to automate. So here what we do, basically the exercise we've done is just taking a forestry operation problem, which is trying to, get the head to move, identify where to move the head in the environment to cut a tree. And we basically translate it into a pure computer vision problem. So in the end, what you have is, let's say that you're using a camera as a sensor. So the system sees this picture, and what you want to find is, where do you cut the tree? Especially like at I don't know where elsewhere in the world, but in Quebec, there's strict regulation about where you should cut the tree. For instance, the stump must not be higher than 15 centimeters. So it's important to be able to not only get, to cut the tree, but also not leave too much stump on the ground. Otherwise, you might get fined by the government. So this is our computer vision problem. Find this cut point in an image. Of course, we can do more than just RGB images. We're interested into seeing, using stereo, RGBD, which would be, stereo, if you want to know the form of stereo, or also using like pure LIDAR systems. We're not starting this project completely blind. We've already have a fair amount of experience doing parallel gripper automation. So we're now up to our third generation of approach to do grass detection. So we use sparse coding and ResNets, and more recently transformer networks. So the last two are based on deep learning. And you can see here the results of the latest work, which was based on spatial transformer networks. So what I think was interesting from Alexandre's work is that he only used synthetic data to train the network to be able to do the grasping, and it worked the first time using a real robot arm and a real camera. So that was pretty impressive. And because we're using deep learning running on GPUs, we're able to get real-time performance. Doing a grasp evaluation takes about 24 milliseconds, which is pretty fast. So computation is no longer an issue with deep learning, and also these systems, because the GPUs are so cheap now. So what Vincent is doing here is trying to see, can we use standard object detection networks to perform this cut point detection in an image. So we use an approach based on faster RCNN. And basically is you have a CNN backbone that goes and takes a complete image, and you have a small network that's called a region proposer that will propose several regions in an image. For instance, we'll propose a region like here that should contain a good the object which you are interested in. Our case, we're interested in finding the base of trees, and the region proposal will find a number of these regions which correspond to different trees in the image. But if we focus on a single region here, you also have a regression head on these faster RCNN that allows you to regress a value. And in our case, what we're looking at is basically using this regression head to find in this proposed region where is it that you should cut the tree. I like this quote from Jitendra Malik that says, labels are the opium of the machine learning researcher, and we're all addicted to it. We need good labels in order to train our system. But the problem is getting labeled data is quite challenging. So what we're looking at is using a stage approach where first we would use simulation data, which is quite cheap to generate, and you have perfect ground truth to train a system. Then after that, using what we call assisted labeling, where you have, for instance, we go in the forest with a stereo camera, and then we rebuild the 3D map. And what we do is you simply annotate on the 3D model the different cut points on your 3D models. And what you do after that is you reproject these cut points into the RGB images. And that way, with a fairly reduced number of clicks, you're able to get quite a large vision database. You can see here the results of such an approach, where we get a lot. Basically, I don't want to say like labeling for free, but the throughput is quite high in terms of how many images you can get using such an approach. But obviously, it's not perfect. You'll see that sometimes the cut point is not exactly in the center of the tree. So you can think of that as simply as being a label noise. So it might be in the end that we have also to use manual labeling of images, which will have a much higher precision, but the amount of data that we'll have to manual label will be greatly reduced because of all the previous data we use from simulation and assisted labeling. So that's the stage approach. Finally, we look at guided navigation for forwarding, which is certainly not a concept that we're the first one to think of. Again, fantastic work by Ringdahl, where they really were ahead of their time when they thought about what is the easiest thing to automate, and it was they really focused on the forwarding. Obviously, because it requires less on the perception side, and also navigability has been established beforehand by whoever was driving the vehicle in the first place. And so again, if you want, we're trying to revisit this work, um, and this time we're thinking about using a technique called teach and repeat. A fair number of people have come up with this idea of replaying previous trajectories. They follow the past by Hellstrom, Ringdahl, teach and repeat by Marshall, Barfoot, and Larson, and also homing from Strom, Bogrovsky, and Strachnis. That they also came up with the same concept, more or less. So the teach and repeat, for those who are not familiar with, is you have a teaching phase where you take, for instance, a local scan of the environment, and as your vehicle traverses this environment, you record the location of the vehicle in that local scan. But eventually you reach the end of your scan. So what you do is you take another scan, and then you do the same game again, and so on and so forth. So what you have is a collection of small local maps that you can use then to replay the trajectory. So in the repeat, what you do is, again, you go to your local scan, you do some kind of error estimation to see how much you depart from your original path. In this case, we use ICP, iterative closest point, because for instance, they could be LIDAR scans. And then you correct the trajectory, and eventually you reach that, the end of this local map. And simply what you do is you just load the next scan, and then you replay the trajectory, and so on and so forth. So this is a very, very nice approach. It's very robust, and also you don't need a globally consistent map. Which means that you don't need to have a perfect view of the environment in a global manner. All you need to do is locally, can you can you locate yourself? Do you have a good map locally? The rest is not important. So what happened when you start thinking that way is, as your equipment, which is driven by non-expert. When I say non-expert, is they're not roboticists, they're not AI people. They just drive their equipment. For instance, the harvester goes and cut trees, so it has to go and traverse the environment. And then if you record the path of this harvester, so in the end you create this, as you can see in blue, this virtual roadmap where you can go and hook on, if you want, a forwarder that would go and basically traverse the terrain again, just like the harvester did. And it also had the benefits if you're able to automate forwarding in the province of Quebec. You have to be able to demonstrate that your harvesting and skidding trails are limited to 25% of a harvest block to reduce the amount of damage on the soil. So by automating these tasks, you're much better able to guarantee these strong requirements. And we've done some tests in 2016. That was David Landry, a master's students, who you can see here in the video, there's 2 takes that we basically overlay on top of each other. So when you see the robot, which has kind of like we have a double vision of a robot, that's because there's a small error. But overall, we found that the performance of such a simple approach was pretty impressive. We had a final error of about 2 centimeters in the localization. And even though there's roots in the ground, the robot sometimes might skid a little bit. The performance were quite impressive in my impression. It's also naturally very robust to occlusion when you use a 360 LiDAR. You see here, David was trying to confuse the robot by walking near the robot, but the robot, is able to filter out David out of the scans and really focus on the trees. So for the guided navigation, we're lucky we found a great student, Olivier Gamache, and basically what we're trying to see is, what are the good sensor suites to use in the forest? Should we use LIDAR? Should we use cameras, the GPS? And also take into account how the environment changes over time. Because, if the time we do the recording of the path is, at the beginning of a season, and then we're trying to replay the trajectory at the end of a season, how is it going to affect it? And also, the map might have been built when the trees were standing. If we do a logging, then there's only stumps left. How can we leverage these older maps to be able to do this repeat phase? Also, things like, it's the impact of dirt or scratches on the optics. It's a very harsh environment, as you know. And deep learning being one of the things we like to do is, is there any way we can exploit semantic information in our maps to make this replay phase more robust to changes? So just to give a conclusion to this presentation, there is great needs for automation in the forestry industry, and also I think from a scientific point of view, the forestry setup, it provides for very interesting challenges due to the unstructured nature of the environment. And we're really here trying to see, how can we take what's already existing out there in the toolbox of AI and robotics, such as deep learning and 3D mapping, to be able to solve some of the issues of the forestry industry. And I think, in the end, there's great potential for key forestry operation automation, such as grasping of trees, which are quite cognitive. The cognitive load is quite high for an operator, and also, again, jumping on the bandwagon of what's been done before, trying to demonstrate again how forwarding can be automated using the approach such as teach and repeat. I'd like to end this presentation just by giving a big thank you to everybody who's been involved in all these projects, people at Nivio like Bruce Talbot and Erasmus Astrup, or people at the Damas like Professor Brahim Shaibdra and Patrick Dallaire, and also all the students, as well as the NORLab, where we currently are doing this new and exciting project. And you can see by the number of faces, it's been a lot of work by a lot of great, fantastic people. So I'd like to give them a big thank you, and also give a thank you to the organizer of this workshop. And particularly, I can imagine that with all the changes that's been done quickly, that they must have worked really hard to maintain the high quality of this workshop. So I'd like to give them a thank you for that, and also thank you for giving me an invitation for this workshop. So I guess I will be taking your questions when the live sessions happen.